Welcome everyone to the UFRGS Astronomy Seminar Series that is held every Wednesday since last week. We have organized talks with amazing speakers from different parts of the world and covering a variety of very interesting topics. This week we have who is a research fellow at the University of St. Andrews in the UK, working with the KEOPS and HARPS-N consortia on the detection and characterization of long-period, low-mass planets using ultra-high precision photometry and radial velocities, observations with the aim to study bulk densities and internal structures of these planets. He completed his PhD at the University College London, primarily studying post-main sequence planetary systems around white dwarf stars using Spitzer and Hubble. Tom, let's start the talk.
Okay, thanks. As a postdoctoral research fellow at the University of St. Andrews in Scotland, I would like to thank for the invitation to talk to you today about exploring the exoplanetary zoo with KEOPS and HARPS-N. On the title slide here you can see a nice artist's impression of KEOPS, what it looks like. It's about a washing machine size, clearly observing a planet transit in its primary mirror here. So here is my outline of what I want to talk to you today. First, I'm going to summarize a brief history of exoplanets, including some notable early detections, and then highlight some of the detection methods we have. And then for the bulk of the talk, I'm going to present first the transit method, go into a bit more detail on what we can learn from that method, and talk about KEOPS, the spacecraft, and some early results that we've been getting from the observations we have. Then I'll transition on to talking a bit about the RV method, and again what we can learn from RV observations, and then a bit about HARPS-N, which I've also been using to get observations of exoplanets. Tying this up and learning what we can do when we have both precise radii and masses, as I'll get onto, I'll then go on to discuss the exoplanet zoo and what we can learn both from an individual planet standpoint and a more demographic overview. And then if I have any time at the end, I'll briefly touch on maybe some next steps in the field or some future prospects for what we can learn going beyond planets in these exoplanetary systems. So first up, a brief history of exoplanets. So they have been thought about for millennia. Actually, we can go back all the way to ancient Greece, where Epicurus, in a letter to Herodotus, said, "It is not only the number of atoms, but also the number of worlds that is infinite in the universe. There is an infinite number of worlds similar to our own, and an infinite number of worlds that are different." So you can see this is kind of the first recorded ideas that we have of people thinking about planets outside of our solar system. Indeed, they might not be infinite now, but at least you had an idea of where we should be going. If we fast forward to the 1500s, an Italian philosopher, Giordano Bruno, wrote in his book on the infinite universe and worlds, "There are therefore countless suns and an infinite number of worlds orbiting them, like the 7 worlds orbiting our own sun." And this is Giordano on the right here, quite a dapper looking fellow. Unfortunately, many of his contemporaries didn't agree with his ideas at the time, but they have survived to this day. In a groundbreaking 2-page paper in the 1950s, Otto Struve, motivated by recent upgrades to the Mount Wilson telescope in the US, kind of put together a seminal work that outlined how we could detect exoplanets. He first went on to predict the radial velocity variation that we would need to detect Jupiters around sun-like stars, but then goes on to also say that there should be no reason why hot Jupiters shouldn't exist. And therefore, if there are hot Jupiters, these planets would be transiting would be orbiting so close to their host star that they should, in fact, occult or transit their host star, dimming the amount of light we see. So it's really a kind of seminal paper. In 2 pages, he lays out basically the entire field as we know of it today. If we jump forward again to the 1980s, many groups were aiming to detect brown dwarf companions to main sequence stars, including Dave Latham and collaborators in 1989 when they reported a companion to this star here. You can see the title of the paper on the left, and the data they reported on the right, with the clear RV radial velocity variations seen. Now, when they were fitting this, they got a minimum mass of 11 Jupiter masses, which is just on the deuterium burning limit, but they concluded that it was probably a brown dwarf, but could also be an exoplanet. With Gaia, we've realized in recent years that this is most likely a brown dwarf, but this is kind of really showing leading the field to push to find exoplanets in the 80s and 90s. So then, of course, along came 51 Pegasi, with Michel Muir and Didier Queloz finding a Jupiter-like planet around this star in 1995. Here you can see the plot on the right, which shows the radial velocity variation plotted against time, in this case phase folded, with a clear planetary or clear radial velocity trend seen, which they modelled and found a Jupiter mass planet on a 4.2 day orbit, which got them half of a Nobel Prize last year. So since then, there have been a lot of missions, a lot of notable exoplanet missions. Some I just want to highlight here include one of the leading photometric transit studies to start with, WASP, which is over here on the left. More recently, we've also had the TRAPPIST observatory down in Chile. On an RV side, we've had HARPS and its Northern Hemisphere counterpart HARPS North, taking precise radial velocity since 2012. And more recently, the Espresso instrument on the VLT, which is kind of the next generation of high precision RV instruments. We're not just limited to ground-based instruments, though. We've had a lot of space-based telescopes, including the Corot mission, which launched in 2006, followed quickly up by Kepler and TESS, which have done a lot of groundbreaking work detecting a whole host, thousands of exoplanets. Currently we have CHEOPS flying, which I'll talk a bit about later. Within the future we'll have Plato and Ariel, as well as others such as the James Webb Space Telescope. So the exoplanet zoo contains about 4,000 planets. As I mentioned, the majority of these have been found via the transit method, thanks to Kepler and TESS. But around 900 have been found with radial velocities, and about 200 have been found with other methods such as direct imaging and microlensing. However, with these 4,000 planets, these systems have quite different architectures. In this quite nice animation by Hugh Osborne, he took all of the planets we knew about in 2017 and plotted them onto a hypothetical single planetary system. So you can see all of the inner planets that we're seeing, that we've detected. This is increasing in semi-major axis, so now we're at about 0.1 AU. You can see we found a lot of inner planets that we don't have in the solar system. For example, this is mainly due to observational biases, which makes them easier to detect for us, but it's still quite interesting that they should exist at all. If we go further out, we can see the orbit of Mercury and several very high eccentricity orbits. We have Venus, and coming up Earth, and then Mars. And what you can see here is that there are a lot of planets on a lot of different orbital paths, and therefore there are a lot of different system architectures that we've detected different to our own solar system, which is pretty exciting. We found a few out all the way to Jupiter and beyond, mainly from RV, direct imaging, and gravitational microlensing methods. So as I mentioned a few times, we have a range of observational techniques to discover and characterize these exoplanets. The main one that I'll be talking about today is transit photometry, which I'll go into more detail in a bit. This can give us a whole range of information, as I'll detail, but mainly the planetary radius. We also can use radial velocity variations, which I'll also discuss, that can give us a handle on the exoplanet mass. A few of the others include microlensing, which aims to measure the brightness of the exoplanet host star to see if there's an additional bump in the brightness due to a microlensing of a planet in addition to the host star. There is direct imaging, which is quite straightforwardly just taking images of a planetary system and seeing if such a planet is there and or moving on a Keplerian orbit over time. And astrometry, which is measuring if the position of the star changes over time thanks to the gravitational perturbation of an exoplanet. So let's move on to the transit method and CHEOPS. So, as I'm sure many people know, but just to give a introduction to those that don't, the transit method is when a exoplanet passes in front of its host star and causes a dimming of the amount of light that we see. So you can see in this nice animation here, this planet has come between us and its star, and the amount of light we see on this kind of cartoon plot down the bottom has decreased over time. We first see an ingress when the light decreases, and we're about to see the egress of the transit as the exoplanet leaves the stellar disk. So that's all a transit is. Quite straightforward, really. But there's a lot we can learn from transits. If we take example dataset here, and this is just a test dataset of the object TOI 101.01, or WASP-46b as it's also known. And what I've done is just simply plot the flux that we have for the star from tests against time. And you can see in this time window we have 3 transits. So what can we learn about this planet from this dataset? Well, first things first, we can get the depth of the transit. So as I mentioned before, when the planet goes between the host star and us, it blocks out a certain amount of light. Now this is proportional to the relative radii between the exoplanet and the host star. And so if we know the radius of the host star and we know the depth of the transit that we can measure, we can get the planet radius. However, this depth to planet radius conversion depends a lot on knowing the stellar radius. And this has come up in a now famous quote in the exoplanet field, "Know thy planet, know thy star." To kind of highlight this, what I want to show over on the right side here is that if we take the same planet and we put it around a G-dwarf star, so a solar type star, what we're going to get is a relatively shallow transit, because the ratio between the planet and the star radii is quite low, but also a very long transit. If we take the same size exoplanet and put it around an M-dwarf, which is about half a solar radii or less, what we're going to in fact see is a much deeper transit and a much shorter transit as well. So in order to accurately know the planetary radii, we need to know the stellar radii also very precisely. This can be very important because, for example, when we get precise radii, we might want to do internal structure modeling, which I'll come back to later. And that, and in order to model with some accuracy, we need very high precision planetary radii. So from transits, we can also get the orbital period, and this is again quite straightforward. We just need to measure the time between the transits, right? This can get a bit complicated in multi-planet systems, where you have to be sure that the transit you're seeing is for the planet you've ascribed it to, and so usually what we do is wait for 3 transits to come along so we can confirm that the period we suspect is the orbital period for the planet is indeed correct. But if we know, especially in this system, there's only one planet that we're seeing, we can confidently state that the time between these two transits is indeed the orbital period of the planet. Now, this can be important because we can convert this period into the semi-major axis, of course, and then if we know the effective temperature of the star, we can calculate then the equilibrium temperature of the planet, which is nicely shown on this plot on the right, which shows the stellar effective temperature on the y-axis going from giants up here at the top down to M dwarfs down here at the bottom, plotted against the starlight received on the planet relative to the sunlight on Earth. So you can see Earth is put here at 100%. Now, why this is nice to, if you have the orbital period of your planet and you have the effective temperature of the host star, you can put it somewhere on here. There is, and then determine if the planet is within the habitable zone. There is also important atmospheric studies that can be done if you know the equilibrium temperature of the planet, and I'll touch on a few later. Also, with timing, as well as just getting the period of the planet, if we have variability in the timing, we can learn something more about the planetary system itself. So in this animation on the left, we have a single planet going around its host star, nicely transiting, and what you'll see is that this should return on a Keplerian orbit. This should return on a period that's relatively well defined, so it should come back exactly when we expect it to do, as kind of shown by these stopwatches here. Now, if we don't have a single planet system, if we have a multi-planet system in a certain configuration, for example an orbital resonance, what can happen is that the gravitational interactions between the planets can cause the timing of the transit of one of the planets, for example the inner one here, to be different and in an observable way. So, for example, the first transit here appeared a bit earlier than we would expect, and then the second was a bit later, and so on and so on. Now, this transit timing variation that we're seeing in this animation is detectable for some systems. Not all, and it is quite rare to happen, but it's been seen a handful of times, including in KOI 872b, as shown on the right here. For example, the top transit is occurring exactly when we expect it to be, so it's on this grey dashed line. The transit is appearing earlier than we expect, and then later, and then earlier, and then later still, until it comes back to what we expect. Now, if we plot these all together and we do some dynamical modeling in the system, we can actually get the masses of both planets from just simple transit timing variation. This is additional to masses we can get from radial velocity observations, so it can be a nice check if we have both sets of data. So those are the main things we can get from transit observations, but let's go on to talking about CHEOPS. So this is the instrument itself before it was launched down in a clean room. I think it was in French Guiana, or maybe it was up here in Bern. You can see it's quite small. It has a nice cover, orange cover on the front, and a very proud principal investigator standing next to it. Here you can also see the 30-centimeter mirror, so it's quite small in terms of ground-based telescopes, but when we go to space everything is more expensive, and so we can launch these smaller telescopes, which still do amazing work. You'll notice that there are these structures holding the secondary mirror in place here. It's kind of blocking out the center of the primary. It was launched on December 18th from Kourou in French Guiana on board a Soyuz rocket, as you can kind of see in this slightly blurry plot here. Then Christmas came and went, and on January 29th the cover opened and we got our first light in a very exciting and nervous moment. So you can see the field here with our target right in the center and some background stars around it. This is now blown up so you can see the structure of the PSF with this now characteristic triangle shape, which again comes from the struts that I showed you in the previous slide. So all of this was looking very well and very promising back in January. We then went through in-orbit commissioning and got our first light curve of a bright, which is a V of 9 mag star, and quiet star, meaning there is very little stellar activity, but also no exoplanet transiting this star. So you see a still frame here at the top left and a movie of the observations here at the bottom left, and our nice flat light curve here, which we could estimate the noise from and get down to 10 parts per million over a 6-hour time window, which is exactly on specifications. So it looks like KELPS is doing pretty well. But we don't just want to measure flat light curves. KELPS was built and launched to get precise exoplanet radii, so that we can do so that we can get precise bulk densities and therefore go on to do internal structure modeling to determine what these planets are made of. So moving on from getting from doing our in-orbit commissioning, we took some observations of our first science target, which is KELT-11b back in March. KELT-11b is a Jupiter-sized planet, as you can see in this comparison between the Sun, Earth and Jupiter and the host star and KELT-11b itself. It's a V of 8 mag star, so it's very bright. So it would therefore provide a very good test case to see what kind of precision we can get on the planet radius. And this is what we obtained. Again, on the left here, we see some animations of the observations themselves. And on the right here, we see a beautiful transit of KELT-11b. So in the top subplot here, we can see the light blue is the raw data, the dark blue is the bin data, and the green and brown overplotted lines here are both a transit model and a stellar variability model as well. So we can clearly see a nice ingress and then a curved bottom of the transit, which is due to limb darkening effects of the host star, and then a clear egress, all very nicely defined, which meant that we could get radius of the planet to the radius of the star ratio that's very accurate, which translates into a planet radius of about 1.3 Jupiter radii plus or minus 0.025, which is a precision of about a couple of percent or something like that. So this is exactly what we were hoping for, and this kind of precision on the radii will help us for modeling the interior of these planets, as I'll get into in a bit. Translating this from Jupiter radii into SI units, we can see that this planet has a radius of about 91,000 kilometers with an error of 747 kilometers. Now, if we, this is kind of now on more human distances that we can kind of wrap our head around this error bar, and if we do that, what we can say is that we now know the error on the radius of this planet to more precision than the straight line distance from Porto Alegre to, for example, Santiago, about the same distance to, or a bit longer than the distance to Brasilia. So this is quite astounding now that we can know this Jupiter radius that well. Now we'll again turn into more precise bulk densities and help us to understand the structure of this planet. So moving on from CHEOPS, I want to talk a bit about the RV method and HARPS-N. So as again, I'm sure many people know, but just to get everyone to the same place, radial velocities, they occur when a companion to primary or host star, this can be either stellar or planetary in nature, is orbiting the primary and gravitationally perturbing it so that it moves around a common center of mass. What that means is that the light from the host or primary star will be blue shifted and red shifted over time. So as you can see in this nice animation here, the black absorption features in the spectra at the bottom are being shifted to the red and then back to the blue. Now, if we take an observation of a exoplanet hosting star, we can measure the radial velocity offset. And if we do this many times, then we can build up an RV time series and learn about the exoplanetary system. And this is what I'm showing here. So this data set is actually the radial velocity time series that won Michel Mayor and Didier Queloz the Nobel Prize last year. The observations of 51 Pegasi that they took back in the mid-1990s. And what we can derive from this quite straightforwardly, there's a bit more work that goes into obtaining RV or measurements from RV data than for transit data, but what we can obtain from this, for example, is the planetary minimum mass. This is done because the maximum RV shift here, you can see this value k, is given as the sampling amplitude of the observations, and putting this into a mass function means that we can derive this minimum mass of the planet. This is simply coming from the fact that larger planets or stars will gravitationally perturb the light or the primary star more than lower mass planets or stars, and so this amplitude will be related to the mass in that way. We can only get the minimum mass because we don't know directly from RV observations the inclination of a system, but if we combine it with transit observations, in which we can get the inclination of a planetary system or of a planet, then we can resolve this and indeed get the mass of a planet. From RV observations, we can also get the period. It's a little bit more complicated. We have to do some periodogram analysis. The data for most systems don't come down as nicely as I'm showing it to you here. We have to do some analysis and then phase fold the data, but you can clearly see that if we go from one peak to a peak or trough to trough, then we can get the period of this planet as well. So a look at HARPS-North. This is the instrument I'm showing in this image on the right. It is a fiber-fed shell spectrograph on the 3.6 meter TNG telescope in the Palma, Spain. It's been operating since 2012. And the instrument itself is housed in a temperature and pressure controlled environment, which means that it can reach a spectral resolving power of 115,000, which is very high indeed. So this means that using HARPS-North, we can get down to a semi-amplitude precision of about a meter per second, which it allows us to probe very low mass planets or planets to a high precision indeed. To put that in some kind of context, walking speed is about a couple of meters per second, so we can measure the gravitational perturbation of a host star by its exoplanet down to walking speed, basically, which is quite fantastic, really. Since 2015, HARPS has also been used to observe the Sun via a small solar telescope on the exterior of the telescope, or of the main telescope, and I'll come back to that in a couple of slides later. So I just want to highlight a few notable discoveries. One was the characterization of the first rocky Earth-sized planet KELT-11b back in 2013, as you can see on this RV time series plot over on the right. It was also the instrument that discovered the 5-planet system HD 219134 in 2015, which is only 20 light years away, and was one of the closest and brightest multi-planet systems known at the time. Multi-planet systems are quite unique because you can do a lot of comparison exoplanetology between the planets, as they should form from the same protoplanetary disk. So having one so close by is very useful for further studies. And then last year there was the characterization of the different twin system, Kepler-107, that has two planets of similar radii as found by Kepler, but significantly different masses. And the team proposed the idea that this could be due to a giant impact between the two planets, and therefore this is kind of one frame of the simulation showing that maybe all of the heavier elements, so the iron of the core of both of the planets prior to the impact, was transferred to the more massive body, whereas a lot of the light elements were retained by the less massive body. So I mentioned before HARPS is getting down, or HARPS North is getting down to 1 meter per second, but what does that actually mean when we're talking about planetary mass? So here I'm showing a plot from Deborah Fisher showing the planet mass, or minimum mass, m psi I, against year of discovery, just to kind of show how far we've come over the last 25 years or so. So we start up here with a few detections of Jupiter-sized planets, or Jupiter mass planets I should say, with over time more sensitive equipment coming online that drops it down to Neptune masses and then further still. Now in the last decade or so, we've been pushing down to Earth-sized planets. This plot is slightly misleading because while we've gone down to about a meter per second, and it's in fact been called the meter per second barrier because we've stayed at this precision for quite a long time, we've refined our observing strategies so that in more recent years we've been able to get down to lower mass planets by looking around lower mass stars such as M dwarfs, and that's why we're also seeing more Earth-like mass planets detected in the last few years. So this is kind of relating the precision to what kind of planets we would detect. Now, as I said, we're getting down to Earth size. However, one of the major problems facing the field in the upcoming years is stellar activity. So here I'm showing the HARPS North solar data from 2015 to 2016 with radial velocity on the y-axis. The observations of the sun are plotted in the back in orange. And what you can see here, this scatter in radial velocity is likely due to stellar activity. So not simply flares or coronal mass ejections, but the day-to-day activity occurring in the sun. Now this has an amplitude of about 10 meters per second, which is quite limiting if we want to understand, or if we want to find Earth-like planets and get accurate masses for them. So overplotted here you can see what the Earth signal would look like if we were trying to detect it, and this is down to 0.2 meters a second. So in order to kind of dig out these signals from sun-like stars and find true Earth-like planets, and even better to get accurate masses for them, we really need to understand stellar activity better, or find a way to disentangle the observations of stellar activity from an orbiting planet. And there's quite a lot of work going on in that regards at the moment. So now we have our accurate radii and accurate masses. Let's have a look at the Exoplanet Zoo. So first off, this is quite a nice plot I like to show that plots all the planets we found as of, I think it's this year, with their orbital period on the x-axis and the radius on the y-axis. Now there are some interesting things to note here. All of the kind of creamish dots down here are objects found by Kepler with the transit method. You can see we found a whole host of planets using Kepler. There's some higher mass planets that were detected via ground-based transit surveys up here, and a lot of radial velocity detected planets found in blue, specifically at higher masses, but also going out to larger orbital periods. Now there's a couple of features you might notice immediately. There seems to be this gap of exoplanets down here. Now this is not the fact that exoplanets but rather this is an observational bias that we haven't had we don't have the instruments sensitive enough to detect planets at these orbital periods and these radii. Another feature that I'll come back to later is this somewhat gap here between the Jupiter planets and the Earth-like planets, very close in, which we don't think is an observational effect, because again we're detecting higher and lower mass planets close in to their stars, so there seems to be this Neptunian desert coming here, which I'll talk about in a few slides' time. So we've got our accurate radii and accurate masses. What is typically then done is throw them onto a mass radius diagram, which is quite a useful tool for learning a bit about planetary structure. And this is what I'm showing here. So this is the plot actually from the different twin system I mentioned earlier, Kepler-107. You can see the authors have plotted the 4 planets of the system along with some other planets with high precision observations. And in the solid lines, they've plotted models of the bulk density of these planets in order to kind of learn something about their internal structure. So in red, we have planets of 100% iron. In orange, we have, if they are 100% rock. And then we have 50% water, 100% water further up here in these lower density regions. So this is a useful tool for just getting an idea of what your planet is looking like, basically. But we need to kind of go further, and this is where improving the radii and masses can help. Because if we have very accurate densities, we can give over to our modeling friends, and they can tell us what is the likely internal structure of these planets. So for example, we could have rocky super-Earth sized planets, but until we know more precisely their densities, we don't necessarily know if they are going to be massive solid cores with a thin atmosphere, or if they're going to have smaller cores but with a larger volatile envelope. Going up in radii, we don't necessarily know if mini Neptunes would have a solid core followed by an ice mantle and then a hydrogen or helium envelope, or if there are no volatile envelopes and it goes straight from a solid core to a hydrogen and helium envelope. And then further pressing questions out in the giants, what is the core to envelope size and mass ratios? Is it something with do these planets have larger cores compared to their envelopes, or are they smaller, and does this depend on the size of the gas giant and mass of the gas giant? So there's a lot of work that can be done, both observationally and theoretically. Moving somewhat onto the demographics of the exoplanet zoo, from a few years back from B.J. Fulton and collaborators that showed taking data from the Kepler spacecraft and plotting the planet size against stellar intensity. They found that there's 2 seeming peaks in this distribution, one at larger radii and one at smaller radii. If this looks somewhat non-convincing for you, then we can collapse this data against the planet size axis and produce this 1D histogram showing the peak of planets with radii about 1.3 Earth radii and another peak at about 2 Earth radii. These have been interpreted by the community as being super Earths, so rocky-like exoplanets, similar to the Earth in density and atmosphere, and more mini Neptunes, so similar to Neptune with a smaller fractional core and then an expanded envelope. But you'll also notice that there seems to be this radius valley in the middle. This is one of current research interest to determine if this valley can be due to planets forming in a gas poor environment, and so there could be a handful of planets that don't simply accrete as much hydrogen and helium to puff up their radii. Or maybe it's the reverse, and they started with a larger radii, but due to photo evaporation, the atmosphere has been lost, and they may fall into the terrestrial-sized planet, should we say, this lower bin here. I want to touch briefly on the Neptunian desert. So as I mentioned before, there seems to be this gap at smaller orbital periods and around the mass and size of Neptune. So this is therefore being called the Neptunian desert. This is currently unknown why this seems to happen. We don't think it's an observational bias, as I mentioned before, but this could be caused by differing formation mechanisms between higher mass giants and lower mass rocky planets. But one exciting result from this year was the discovery of TOI 849b, by Dave Armstrong and collaborators, that found a planet with a mass of 40 Earth masses and a radius of 3.4 Earth radius, with a determined period that put it right in the middle of the Neptunian desert. This characterization, or the characterization of this planet, also gives it a bulk density similar to Earth, which the team suggested why it could be a stripped core of a giant planet, which has been proposed to be due to atmospheric stripping due to impacts, for example. In the brief time I have left, I just want to highlight some work that could be done in the future beyond exoplanets. So the next generation could maybe use more precise instruments to find, for example, exomoons. There has been one tentative example a few years back that showed an potential exomoon, although it's not clear and it's somewhat hotly debated, but there is no reason why exomoons shouldn't be detected, likely with more accurate photometry missions. In addition to exomoons, what about exorings? Well, there is this one system, J1407b, that has been modeled to be a planet with a massive 1.2 AU wide series of rings, somewhat akin to Saturn. If this is correct, this will be the first exo-ring system. But again, this could be a future path for the field. In Beta Pictoris, there have been exocomets observed both spectroscopically via radial velocity offset calcium H and K absorption features, also photometrically using the TESS spacecraft to find these asymmetric transit-like features. So aside from Beta Pictoris, more work could be done looking for exocomets via these methods. And I would be remiss if I didn't briefly mention at least looking for exo-asteroids. These have been found around many white dwarfs to date, with transits seen at least 2, but I'm sure there'll be more to come. With both photometric and spectroscopic emission from circumstellar material and spectroscopic absorption from atmospheric metals also providing evidence for planets around white dwarfs. So this is a very fertile, rich area of exoplanetology. So I just want to conclude here and say thanks for listening, and I'm happy to take any questions, but before I do, I just want to highlight that if you are interested in KELT-11b and the high precision photometry I've shown, then there is a second annual announcement of opportunity for the guest observers program that will be opened in November of this year for about 4 weeks. So you can apply for your own programs for whatever targets you want, provided they are not on the protected list. But that list is public and is primarily exoplanet hosting stars. If you can't wait until November, the discretionary program is open. now, so you can, if you have an exciting target you want to get high precision photometry on, you can propose for discretionary time. If you'd like any more information on CHEOPS in general or on proposing for time, please feel free to ask me a question or contact me on this email address. Thanks.